Okay, today we're going to try to understand the mold concept, and these are my steps for getting there. And it's got some visualization techniques that you probably won't get elsewhere. And the first thing that you need to accept, and it's not technically Avogadro's law, it's some other guy called Guy Lusax. He basically noticed that when you started mixing volumes of gases, they always reacted in the right ratios. And if we just go over to the diagram, so the first one is it's his initial mixture, but one he performs the experiment at 25 degrees, so that's when water is in liquid form. And so he's mixed 20 mils and 20 mils, and he gets left over 10 mils of oxygen. He goes, oh, okay, interesting. And then he repeats that at 100 degrees and notices that he gets 10 mils and 20 mils. Okay. And so he's like, all right. So I've obviously got 10 mils of hydrogen reacted. And he's basically playing around with all these kind of things. And what you need to get out of that is what I've got in yellow down here. That basically 2 liters would react with 1 liter to get 2 liters of water, and you would have nothing left over. And how you'd know that's all water is you'd change it back down, the temperature to below 100, and you get it all into liquid form, and you get basically a very small volume of gas. So I think it's about a thousand-fold expansion. So you get something like 2 mils worth of liquid or something. 20 mils of liquid, I should say, because that's 2,000 mils. No, sorry, 2 mils of liquid. My bad, my maths. And if you then just put in a tiny bit more of hydrogen gas, that won't react and would still be there at the end. And again, you can play around in terms of temperatures, and the same thing with oxygen. So you walk away with the conclusion that volumes of gases react in the right ratio. And the inference of that is that it must contain the same amount of particles. That is to say, 1 liter of oxygen contains the same number of particles as 1 liter of hydrogen when in gas form. Okay. And that's very useful. So the next step is going, okay, that's all well and good. Not all reactions happen in gas form. Can I get that to a more convenient form, which is mass? I can measure the mass of a solid, liquid, and gas. So much easier in terms of working with particles. And here's the clever, you know, bridging gap. And essentially all they need to do is pick any element, any amount, and they just go, here's my reference. And then what they've chose, and this happened in like 1960s, this like International Union of Pure and Applied Chemistry, they chose 12 grams of carbon 12. And there's a lot of reasons why they picked that. Oxygen was their like other one. Carbon 12 is easy to work with. Carbon's in organic chemistry. 12 times divided by 12 gives you the another reason why you can explore atomic mass units. Anyway, it's not relevant to you right now. They chose 12 grams of carbon 12, the isotope carbon 12. Okay, and then all they need to do, this is theoretical, like this yellow drawing, this is just your learning tool. It works in terms of theory, it doesn't work in terms of practicality. I will explain that. Carbon 12, let's say at 25 degrees Celsius, which is what they call room temperature, fairly warm room, and the pressure that you're experiencing now, which is 101.3 kilopascals or 1 atmosphere, if you could somehow turn 12 grams of carbon 12 into gas, you heat it up and it stayed at that temperature as gas form, it would then get funneled into this apparatus. This apparatus is a made up apparatus. This apparatus basically is a cube and it expands based off how much gas is pumped into it. And lo and behold, 12 grams of carbon at this temperature and this pressure expands to almost 25 liters, 24.79 liters. And that's all well and good. Okay. Don't know how many particles are in there, but I know that's how many particles are in 12 grams of that. It occupies that much. Okay. You go, all right, great. The real trick to it, and I'll explain its limitation. Again, this is a learning aid. The real trick to it is then to realize that all you need to do is get any other element, repeat the process, and then weigh the box. Okay. So Let's, for instance, say you did oxygen, you had oxygen, you funneled in oxygen until it reached 24.79 liters. You go put that box, the inference, sorry, for all these boxes is that they contain the same number of particles. You don't know how many particles, but the same number of particles. Again, these are all done at the same temperature and pressure. And you put oxygen on your mass balance and it gives you 16. And that's what's written on the periodic table. And then you go lead. Lead's 207.2. Okay, so lead's obviously these really heavy particles. And sulfur is 32.07. And right now, where should you be at? You picture the same number of particles in all of them, and they all just differ by their heaviness. And this is true. Like, we're going to come back and circle, like, how true is that? It's pretty true. It's not exact. We're going to get technical later, but as a starting point, this is what most chemists work with unless they need to be really, really particular. When you're dealing with the amount of particles in here, and it's like, trillions don't even do it, justifications, like it's like 10 to 6.02 times 10 to 23, like a ridiculous amount. It doesn't matter if you're off by billions or trillions, that's only less than 0.1% of the whole. So as a crude method, this is really, really good. So what you should start picturing is every box has particles. They're all exactly the same size and they just weigh different amounts. So lead's exact same size particle weighs significantly more than oxygen and sulfur because it gives 207.2 grams. And so you could call it more dense or whatever than that. And that kind of makes sense. I mean, lead has 82 protons, has a lot more neutrons. The difference between those two has, 125 odd neutrons. And that makes sense. And that, we're going to come back and challenge that. But basically, picturing them as the same size is a fairly good assumption, even though it's not ultimately true. That's because protons and neutrons take up really, really, really small spaces. And we're going to also assume that they have no interaction with each other. That is to say, oxygen isn't attracted to other oxygens and they're not going to clump together. Same with lead, same with sulfur. We call that an ideal gas at this point. So an ideal gas is basically, they're just little billiard balls and they're bouncing around each other perfectly and they're not interacting with each other and they're just, bouncing around like smooth little balls that aren't chemicals. Okay, all well and good. All we've established is we can deal with boxes and mass. Right. First thing to figure out, you can now make a relationship between mass and the number of particles. First thing, I'm going to go back to this box thing. The box is now called 1 mole. Okay, this box is now 1 mole. It's short for molecular, and it's just another way of literally saying a box. A box of particles, a mole of particles. It's like a dozen. It's just a convenient way to talk about particles as this is a clump of particles, 1 clump of particles. And so you go, all right, what if I had 10 grams of all these different substances? Well, you go, all right, sodium, if I had 10 grams, a box weighs 22.99. So if I have a ratio of that, I pretty much have close to 43% of a box. Okay, so I have 43% of a mole, I have 43% of the particles that are in that box. And same with oxygen. Oxygen's it's diatomic, so you got to realize that you got to times it by 2. So you go 10 divided by 32. If I had oxygen and in a box form, just O2 in box form, I have 10 grams. So if I have O2 in box form, it would weigh 32. If I have 10 grams of that, technically means have about a third of a box of particles. If I had carbon dioxide in box form, it would weigh 42.01. And if I have 10 grams of that, I have close to a quarter of a box. Okay. And we're now going to start replacing a box with a mole. I have about a quarter of a mole. these formulas are going to